and today I'm going to present our project published on WACV 2026. It is mitigating the modality gap, few-shot auto distribution detection with multi-modal model prototypes and image bias estimation. So I'm going to introduce some backgrounds on this project first. Why we want to do auto distribution detection? Usually for machine learning models, we train the models on some kinds of fixed training data sets. For example, we use Alaska dogs here as an example. But when we are deploying the model in real-world scenarios, we often encounter some auto distribution data, for example, husky dogs. And the pre-trained image-based models, usually we're gonna have prediction. But for those like training data, for in-distribution data, we usually can have mostly accurate predictions. But for auto distribution data, for example, husky or maybe other kind of dogs, the prediction might not be very accurate. So the problem we want to try to solve in auto distribution detection is we want to ensure the reliability of our machine learning model, pre-trained image machine learning models, because we want the model to be overconfident on auto distribution data. Also, we want the model to ensure the safety of the model. We don't want the model to misclassify OOD data into any in-distribution patterns. That would give us very bad situation in medical diagnosis and autonomous driving. And finally, we want to make sure that our machine learning pre-trained model is robust. So we want to ensure the consistent performance under the open world scenarios. And how we gonna do with OOD detection? So for image model-based detection, we usually just extract the middle representation of predicted largest, the output of the final data, and then we have some predefined threshold and predefined OOD scores. For example, just using the maximum of the predicted largest to see whether the input data is in distribution or auto distribution. So in this case, the Alaska dog, we might have a very high predicted largest, like 0.9, and for husky maybe 0.1. So the husky will be auto distribution as identified by our model. But the drawbacks of image model-based OOD detection is usually they're closed set. So the model can only classify or detect the data from like in distribution from the already seen data instead of new OOD classes. And also there's a lot of semantic variation. So the image-based models, they have shown prone to low-level noise and textual differences. So that's also a problem. The final problem is usually for image models, because of the limited training data set, they're usually overconfident on near OOD scenarios. For example, in this husky to Alaska scenario, even for human being, for most of the human, they're pretty hard to distinguish husky from Alaska. So how we can record this from pre-trained image models? That would be very hard. And on the other side, researchers have started to explore the use of vision learning model in auto distribution detection. So the first will be the background on vision learning model. For vision learning model, we have a bunch of training class name instead of like kind of one hot vector to represent the data from each class. For example, here we use a photo of an Alaska dog, a photo of a husky dog to represent different classes. And still we use the training like input image to train the model. And we put the training class names and prompts into the text encoder to get the text embeddings. The text embedding will have the shape of 2 by D. 2 is the shape of the number of classes. And we put the image into image encoder to get the image embedding, and we calculate the similarity between cosine similarity between the text embedding and image embedding to get the similarity, and then apply the softmax to serve as the predict logics, the predict classes, like prediction of the input image. And then we, as usual, we minimize the cross entropy loss in this classification or retrieval problem. This is just how vision language model works. And as usual, it is pretty easy to, once we train the model, the text encoder and image encoder, they will be aligned, and we can use as a lot of downstream tasks. As usual, this kind of model, vision language model, for example, CLIP, once they're aligned, once they're trained, they can be used to ask for OOD detection. And still the same, we get the image interdistribution text prototypes, the text embeddings of 2ID. And if our distribution data are Alaska and Husky dots. And once we got the input image, for example, a cat here, and we're gonna calculate similarity between image embedding of that cat and the in-distribution text embedding or text prototypes to see the cosine similarity between them. And a very common use of the auto distribution score is we can use the maximum similarity between the image embedding and the in-distribution text prototypes. If the maximum similarity is higher than some predefined threshold, we can say the input is in distribution. Otherwise, it will be auto distribution. It's just pretty much similar to something we did in image-based OOD detection. So a quick wrap on those methods. So for image-based and VLM-based OOD detection methods, image-based are usually closed set and VLM-based are usually open set, because as long as we know the name of that kind of classes, we can do OOD detection on any dataset benchmarks. And image models, their training datasets are usually pretty limited, but for VLM, because nowadays, due to the success of foundation models, they are usually trained on extensive image text data. And also for image-based auto distribution detection, they have limited interpretability. The OOD scores are hard to interpret, but for VLM-based model, we can have a lot of interpretation on that. For example, if it has higher cosine similarity, that will be easier for human to understand why we did that decision and why we do not have that decision. Okay. Next will be very natural improvements on vision learning models. So when we are applying visual models in some applications such as image classification and auto distribution detection, researchers have observed that the performance are actually dependent on the prompt used for generating the text embeddings. For example, we can see for color type 101, if we use the prompt of a class, the accuracy is only like medium. But if we use the prompt of a photo, like an aircraft, we'll get the highest accuracy. And the same observation we can see on different benchmark data sets, like different prompts, they give us different performance. So this is one very important observation. And those prompts are usually human written and hard coded. So it will be pretty hard to find the optimum prompts for different dataset benchmarks and for different tasks. So researchers recently have developed methods named as prompt tuning to find the best prompt that is useful, that is optimal for different datasets and tasks. So people use, here you can see a set of learnable prompts, which consists of a sequence of learnable vectors to represent those prompts, so that we can use only a small set of training data, and we can update the prompts to learn the best prompts for like each data set benchmarks, and that will be the best for regarding the performance and different tasks. Okay, the next third one, the problem we investigate in this problem is the modality gap in vision learning models. So vision learning models, they're usually pretrained on multi-modal model constructive learning. And we usually have like a modality dependent encoders to encode those data into embeddings, and then we have contrastive loss to minimize the distance between them and update the modality dependent encoders. But the researchers published a paper on News 2022. They found that the representation of two modalities are actually clearly aparted. So, and that kind of modality gap will exist no matter that what kind of initialization we use and what kind of training data and training methods we use. And how this modality gap affects the performance of auto distribution detection, that will be something we want to focus on. So actually we found that the modality gap actually gave us like a very big impact in auto distribution detection, because if the modality gap exists, the OD images they might be close to in-distribution text embeddings. And for example, we use a photo of a butterfly as a text prompt, and we have in-distribution image, which are just butterfly, and there's an like OD image, which is just a flower. But actually, their cosine similarity is something we don't want because the OD image somehow they have higher cosine similarity to butterfly instead of that. Compare between the image in distribution image and like a photo of butterfly. So yeah, this simple example give us some kind of hints that this problem actually give us very high false positive rates in OD detection. So we don't want this problem happen in auto distribution detection. We want to mitigate the modality gap to see how can we have better performance, how can we have reduce modality gap. So to this end, we propose our method, which is named Supreme. It's a very interesting name. So just following the very like general VLM paradigm, we have an input image here, and when we put them into image encoder, we get an image embedding. Then we introduce a new bias prompt generation module, which learn the prompts like suitable for in-distribution image and for that in-distribution data sets. And also we wanted to bias the prompts towards the image. And then we get the image bias prompts using the bias prompt generation module. And then we pass the class names, we add a class name to the prompts, the learned prompts, and we put them into the text encoder to get the text prototype used for like classification and retrieval. So also following the previous method, following the general paradigm, we minimize the cross entropy loss between in-distribution image and in-distribution classes. And the last module we're adding here is the image text consistency module, which is applied to minimize the image and text spatial distance, because in the previous slides we have seen that the modality gap between image and text somehow impact the performance of auto distribution detection, because the spatial closeness does not represent semantic similarity. Okay, next I'll be giving the details of each module. First will be bias prompt generation, how we generate the prompts. So we use three kinds of different prior to generate the bias prompt. The first thing we use here is a domain bias. it is a Gaussian distribution, characterized by mu and sigma. And it is added here for image domain level prior, so that the generated prompts can be biased towards image domain instead of only something on the test domain. And we do sample every run for generalization ability. Just sample a sample B from the domain bias, the Gaussian distribution. The next thing we're adding here is the image embedding. It is here for adding the instance level prior, so that the prompts could be further biased to the image, to the instance, instead of like the general domain level biased. Then we also minimize L2 distance, the L2 loss, the L bias here between the sample B and the image embedding, so that the domain bias could be updated during the training. The last thing we're adding here is the learnable context V. It is a set of learnable vector serving as a soft prompt in generating the image bias prompts. Adding those three things together, we get the final image bias prompts that can be used for generating the text prototypes. Okay, and the next module I'm introducing here is the ITC, which is designed to minimize the distance between text prototypes and image embedding. So let's use dog as an example. We get the dog prompts by putting the dog that word into the text encoder. We get P text dog, P represents prototype, and also one input image I dog here. So we learn two mappings in this module. The first one is text to image mapping, F text dash image. And the second mapping we learn here is image dash text, representing image to text mappings. Those two mappings serve as they're used to map the embedding from one domain to another, for example, from text domain to image domain. So that, yeah, in that sense, using those two mappings, we can map the text prototype into something on the image domain. Similarly, we can map the image embedding on the text space. And the two laws, the first loss we're minimizing here is the inter-modal loss. We want to minimize the distance between the text prototypes and those of that mapped image embedding, because with the F image dash text, we can somehow treat the I dog as something on the dog embedding on the text space. And the same, we also minimize the L2 distance between I dog and P text dog. Then using the same two embedding, same two mappings, we can map the prototype back to the text space, and also the image embedding back to the image space with those two mappings. And still, we don't want to lose any information during those two mappings. So we add an intra-modal loss between like those four representation, the L2, using the L2 distance, so that we can ensure that during those two mappings, nothing is lost and all the information is preserved during those mappings. Okay, so summarizing those two modules, BPG, bias prompt generation, is used for generating the image bias prompts, and ITC is here to apply to minimizing the distance between text and image data. But there's one thing we can observe here. We have the image to text embedding mapping. Is there anything we can utilize so that we can get better performance on OOD detection, and can we design a new OOD scores based on that? So actually, we do have a new designed OOD score based on that learned mapping. We already introduced the impact of modality gap before, which mattered the performance. So instead of only using the text prototypes to understand whether the input image is in distribution or order distribution, we also use in ID image extracted from the training data to obtain a set of image prototypes so that we could identify the input image is whether they're similar to the image prototypes, so that our comparison will not be affected by the modality gap. Okay, so yeah, now we have the text prototypes generated from using the text encoders, and image prototype generating using the image encoder, and in distribution images. We calculate the similarity between image embeddings and text prototypes, so that this is just the like the general things that people did in a visual model-based OOD detection. And then we use the maximum value of that similarity to determine whether the input image is in distribution or not. And the second similarity we utilize is the similarity between image embedding and image prototypes. Because they are on the same kind of space, they're all on the image space. The modality gap shouldn't affect the performance. In the same way, use a maximum value among this group of similarity, and we get that to determine whether the input is in distribution or not. And as I said before, mentioned before, we already trained the image to text mapping, so that we can also use that to map the image embedding onto the text space, so that the modality gap would not affect the performance anymore. Then we calculate the similarity between text prototypes and the mapped image embedding, those two. And those two can be seen as on the same space, because text prototypes are on the text space, and the mapped ones is also on the text space. Similarly, we have the maximum value to help us to determine whether the input is in distribution or not. And the last similarity we're adding here is the similarity between image prototypes and mapped image embeddings. And still the same. We calculate similarity between them and choose the maximum value and use that to determine whether the input is in distribution or not. And this is our final auto distribution scores, which combines the similarity between two prototypes from two modalities, and also the input embedding from two kind of modalities. We can think here, because we mapped the image embedding from the image space to the text space using the image to text mapping here, so that the modality gap could be alleviated. And yeah. Okay, this is just everything about our methods. How are the experimental results? The key results we're reporting is FPR95 and OROC. So compared to the best SOTA methods, we improved the performance from 23 to 20, and OROC from 94 to 95. We also evaluated the modality gap between image embedding and text prototypes to see whether our method is working. So we calculated the L2 distance between the centroids of two embeddings. We see that we did observe that on the in-distribution data, we have a very big improvements on the L2 distance. We reduce it from 0.86 to 0.61. And for widely used auto distribution dataset benchmarks, we also have a reduced L2 distance. Another key results we're reporting here is the T-SNE visualization of embeddings. So we select two classes from the should be a natural list to see how our model works, and class 1 and class 0. So I is the data extracted from just the image embedding, and this is a dash represented the embedding mapped by the image to text mapping. And we can see that, so actually, though they're still separated, but you can see the image prototypes located very good in the image embedding, and the text prototype located very close to the mapped text embedding. Sorry, mapped image embedding here, which means the mapping is very useful, and the modality gap actually still affects this OOD detection problem right now. So the final limitation, the final part will be the limitation of our proposed model. So the first limitation we can observe here is our model still relies on the in-distribution data, which might not be available during all the scenarios if we were just simply applying to the new application. And also the proposed OOD score average the contribution of different modalities. We didn't consider or did a deeper analysis on how the contribution work. So that would be another limitation, actually. And to those two limitations, the first one is we can use syntactic data using diffusion models to generate the inter-distribution data if we couldn't get any of them. And the second solution might be we can use test time adaptation. So during test time, if we see any data, they have very high confidence to be inter-distribution data, we can just think it as like a fake or pseudo inter-distribution data. And for the second one, what I can see for solution here is also still test time adaptation. Is it possible for us to adaptively adjust the importance of each modality instead of just averaging? Because even if we do some like weights or calibrations on different modalities, that would be still, I think, instance dependent or benchmark dependent. So that will be very interesting to see whether we can predict or get some prior from the input data to see how we can adjust the importance, the weights of different like similarities. That would be better. Okay, so that concludes my seminars.